(25) CPS geometry. Similarity theorem in CPS. Space, the final frontier. We all have heard this expression many times over. For better or for worse, this expression has created the impression that space is something existing far, far away. This is why space is mainly understood today as the extraterrestrial frame, where satellites, planets, stars and galaxies exist. The space that I would like you to consider here is that space. But it is also the space that surrounds you. Your day-to-day existence happens in this space. Move your hand, turn your head, open and close your eyes, observe your friends playing volleyball. All these common activities happen in space and involve movements in space. The questions that I would like you to ask next are: what is space? How can we form a concept of space that represents, as close as possible, the physical, real space? Let's try, together, to answer these questions. I suggest we start by reminding ourselves the old saying, divide and conquer. Let's apply this universal rule to the space. This has been done already in geometry and physics. The Euclidean geometry already imagines infinitesimal points, which, when arranged in the proper way, form straight lines. Next, these lines can be arranged to form planes. And finally, planes, stacked on top of each other, form the 3D space. This is, in summary, the concept of space that most of us are left with, after completing our basic education. But, is this approach of dividing the space the right one? Are the concepts needed to mentally create this image of space correct? During the development of science, it has been observed that the power of the scientific method increases once boundaries are imposed on experiments. Also, we have learned that the best way to start to understand a process, or a phenomenon, is to understand how it behaves at the limits. With this in mind, let's identify 3 very fundamental observations and facts that define the space around us. The first observation, made and developed along many years, is that there are a very limited number of perfect bodies that can exist in space. Known today as the Platonic solids or the regular solids, these objects are the tetrahedron, the octahedron, the cube, the icosahedrons, and the dodecahedron. Directly related to this, it has been also found that there are a very limited number of semi-regular objects, 13 to be exact, that are called Archimedes' solids. We have already shown in the previous videos that all the Platonic solids and some of the Archimedes' solids are patterns in CPS. This is also true for the remaining Archimedes' solids. Next, let us look at a great quote from Johannes Kepler. Geometry has 2 great treasures. One is the theorem of Pythagoras, the other, the division of a line into extreme and mean ratio. The first we may compare to a measure of gold, the second we may name a precious jewel. The most fundamental fact about space, known from a very, very long time, is the validity of the Pythagorean theorem. In very simple words, the Pythagorean theorem states that the area of the circle that has as the diameter the longest side of any right triangle, is equal with the sum of the areas of the 2 circles with the diameters equals with the shorter sides of the right triangle. Historically, classical geometry has been born and developed starting from the Similarity Theorem, attributed to Thales of Miletus, around 600 BC. Pythagorean theorem is a consequence of the Similarity Theorem. The Similarity Theorem is more fundamental than the Pythagorean theorem. Euclid is probably the first to realize that geometry is based on the Similarity Theorem. Trying to set on a firm ground this theorem, Euclid proceeds as follows. First, he introduces the definition of parallel lines, see definition 23 of the Elements. parallel straight lines are straight lines which, being in the same plane and being produced indefinitely in both directions, do not meet one another in either direction. Next, he introduces the fifth postulate, or the parallel postulate. If a line segment intersects two straight lines forming two interior angles on the same side that sum to less than two right angles, then the two lines, if extended indefinitely, meet on that side on which the angles sum to less than two right angles. By doing that, in both steps, Euclid indirectly invokes the behavior of the lines at infinite, by using words like produced indefinitely and extended indefinitely. In other words, the concept of the parallel lines and parallelism is closely connected with the infinite, or more exactly with the infinitely large. Today, we use the term Euclidean geometry for the geometry that satisfies all of Euclid's axioms, including the parallel postulate. What we propose now is to understand the parallel lines and the parallelism by looking into the infinitely small, looking into the differential. If we assume a CPS arrangement of points, and if we assume the space as being the result of this arrangement, then the parallel lines can be seen and understood in the infinitesimal small. If we take the CPS approach to the distribution of points in space, then the similarity between two triangles have a totally new meaning. Even more, the CPS approach of understanding and defining similarity also introduces the concept of quantization or of discreteness. This has appeared through the back door in physics at the end of 19th century, and the beginning of the 20th century, when studying the black-body radiation and the quantum effects. In fact, one can argue, this has been already anticipated by Kepler with his unorthodox idea that the orbits of the celestial bodies, in our solar system, are proportional with the sizes of the nested Platonic solids. In CPS, Pythagoras' theorem follows as a consequence of similarity. But once again, the similarity is not based on the existence of the parallel lines, but on the similarity, or the existence of patterns in CPS. The full philosophical implications of this approach are still to be understood. There are two ways to look at similarity in CPS. Case 1. As we have seen, in the close packing of spheres, the structures are fully scalable. A structure will preserve its shape when the radius of the spheres increases. Using the Platonic structure's visualization, one can see that a structure will preserve its shape when the distances between spheres increase. A number, representing the ratio between the two radiuses of spheres, or the ratio of the lengths of the two corresponding rods, can always be used to connect two instances of the same structure. Any triangle will preserve its shape during the expansion or contraction of Platonic structures. One can argue that Thales' similarity theorem can be proven in this way. However, this is not the source of the similarity in CPS we need to be concerned with. Case 2. All the patterns observed in CPS are in fact the manifestation, the cause and the explanation of the similarity theorem. Even the term pattern hides in fact the same idea. Different instantiations of a pattern are connected by the similarity. Usually the pattern is discovered by looking for similarities in instances. Many times, phenomena or things apparently unrelated are connected by the same pattern. Once the pattern is recognized, then we call them similar. Usually, a theory is then developed to explain the newly discovered pattern. The CPS patterns also reveal the quantification nature of patterns and of the physical reality. In classical geometry, the classical similarity theorem does not suggest or consider this aspect. Once one consider an underlying CPS structure for the points in space, then the similarity theorem, and the quantification property of patterns, can be seen as the direct result of the initial assumption, the CPS arrangements of points. The similarity theorem requires the introduction of ratios and proportionality. This of course is possible only if the concepts of measurement, length and areas are introduced first. This also connects once and for all the world of numbers with the space, or, in other words, this connects the arithmetic with geometry. The Cartesian plane has tried to force this connection. The approach it takes looks simple, but the underlying premises introduce errors and they are not able to explain the rich phenomena observed in the physical space. The CPS approach to the similarity theorem provides the solutions to these problems.